Good morning. Today we will discuss about the temperature stress. So suppose sometimes a rod or a bar of a material is subjected to rising temperature or falling temperature, then temperature stresses will develop. So here we are not taking any external load acting on the bar, tension or compression load, just as we discussed earlier. Only we are considering a bar or a rod is subjected to only rising temperature or falling temperature. That means the rod is either heated or cooled. Now, to understand the concept, I have done a diagram here. This end I have taken fixed. That means there is no deformation this side. So it is fixed here. Whereas at the other end I have taken free. There is no support here. So at this end the bar tries to elongate or contract. So elongation of the bar takes place if there is any rise in temperature. I have written here this initial length it will increase by delta L if it is heating. That is your whatever T1, T2. T1 means initial temperature, T2 is final temperature. Delta T is the difference. That is the change in temperature. If final temperature is more than initial temperature, that means you are heating that bar or rod. So now if you heat, definitely at the free end, elongation of the bar takes place. That I have written as delta L. So due to that, what happens? There will be a development of tensile stress. Tensile stress at this length. Because it is elongated, tensile stress will develop here. Suppose if the bar is cooled or if the temperature is decreased, then what happens? There will be a reduction in the length. That means delta L, there will be contraction. Contraction will be there, and due to that, you will be having compressive stress. Compressive stress will develop due to that contraction. So both the cases I have shown in this diagram. So here, for cooling it is T1 greater than T2, for heating it is T2 greater than T1. These are the nomenclature I have used. Delta L I have taken for elongation or contraction, depending on whether the bar is heated or cooled. Then L is the initial length of the bar, E is the end smallness of the material of the bar, and A is the cross-sectional area of the bar. So if you take the cross-section, so this is cross-sectional area A of the bar, it may be circular or it may be rectangular. So it is cross-sectional area. Then I have written sigma T for temperature stress. Of course, it is due to heating, because T I have used for this tensile. Sigma C I have used for compressive stress, so that is due to cooling. So these are the notations, units I am going to follow. Now here, if you observe here, there is an expansion for change in length. So this change in length can be found out using this formula. Whenever a bar is subjected to a heating or cooling, the formula is alpha L into delta T. So here alpha is called as the coefficient of thermal expansion or linear expansion. Its unit is some value, some strain value divided by per degree centigrade. So it is a strain developed by the material per degree centigrade. If the material is heated or cooled by 1 degree centigrade, then what is the corresponding strain in that? That is called as coefficient of thermal expansion. So here, so alpha is that L is the length, initial length of the bar, which is expressed in millimeters. So delta T is the change in temperature. Maybe it is rise in temperature or decrease in temperature. So once you substitute this formula, you will get the change in length. So it can be elongation or contraction. Elongation will be there when the bar is heated. Contraction will be there when the bar is cooled. Now these are the typical values of alpha for different types of materials which we come across. So you can see here for steel, it is 12 into 10 power minus 6 per degree centigrade. That means there will be a strain of 12 into 10 power 6 when 10 power minus 6 when the steel is heated by 1 degree centigrade or cooled, it is cooled by 1 degree centigrade. Similarly, for copper it is 17.5 into 10 power minus 6 per degree centigrade. For brass it is 19 into 10 power minus 6 per degree centigrade. For aluminum it is 23 into 10 power minus 6 per degree centigrade. That's why, that means the alpha value is highest for aluminum among these four materials. So it is the value of alpha. Once you know the value of alpha, L and change in temperature, you can easily calculate the value of delta L in millimeters. Now there are three different cases that will arise in this temperature stress. The first case is allowing the bar to expand freely or contract freely. That is this case. So I am not providing any support at this end. It is restrained only at this end. So there is no deformation at this end. So it is allowed only in one direction. So therefore it is subjected to tension or compression. See here. So same figure I have written here. In this case the formula is same. Delta L is alpha into delta T. So from this change in length, you can always calculate the strain. So this is called as temperature strain here. So epsilon T. So temperature strain. Temperature strain is given by change in length divided by initial length. If you substitute this, you will get alpha into delta T. So that is the temperature strain. Then you can calculate the temperature stress. Either it can be sigma T or it can be sigma C. So here also it can be epsilon T or it can be epsilon C also. So it is given by strain multiplied by Young's modulus. You know that Young's modulus is equal to stress divided by strain. Therefore, strain into Young's modulus gives the value of stress. If you multiply, that means if you substitute here for epsilon as alpha into delta T, that multiplied by E gives the value of stress. So alpha E into delta T gives the value of temperature stress in the case of free expansion or contraction. So normally they will ask you to find either delta L or sigma in the problem. Second case is, suppose if I restrain the bar at both the ends. So both the ends means this side also I have restrained, this side also I have restrained. Restraint means there will not be any deformation. Delta L is prevented. In that case, what happens? If there is a rise in temperature, naturally what happens? If this bar, when you hit this bar, it tries to expand in both directions if there are no restraints at the ends. But this, due to the presence of this restraints, there develops a compressive stress, opposite nature. Here, of course, the formula remains the same. So nature is different, that's all. So the difference between this and this is, here if there is tensile temperature stress that is going to develop, here it will be opposite, compressive tensile stress that is going to develop. In this case, if it is compressive, here it will be tensile. See here, I have given here. The only thing is, the nature of stresses will be different between the free expansion and also the bar which is fully restrained at both the ends. So formula remains the same. Next, third case is partially restrained. This is most important because normally this type is provided in rails. In trains, parallel rails will be there. So there will be a gap here. In this case, this is restrained. This side is partially restrained. Partially restrained means normally they will allow some gap here, delta. Gap or allowance, which is also called as allowance. Some, let us say some 1 mm or 2 mm gap may be provided at one end. So that if there is any rise in temperature, so that this whatever bar is there here in between the two, it may expand to some extent. So, but the total expansion or free expansion, whatever I have shown here, it is nothing but alpha into L into delta T. So among that, from that you have to deduct this delta here because delta is already provided. It is the allowance provided. So that is why it is called as partially restrained. So restraint means complete restraint. Free means there is no restraint at all. Partial restraint means you are going to provide a gap, a small gap in between these two. So in this case, what happens? If it is free ender, then it expands freely. The value is alpha into delta T into L. But I have provided the delta gap here. So therefore, the net expansion delta will be this minus delta. See here, delta L is alpha into delta T into L, which is free expansion, minus the allowance whatever is given. Now, here what happens is this is delta L. If you want once again sigma value for this partially restrained case, it is strain multiplied by Young's modulus. Once again, strain is delta L by L into Young's modulus. If you substitute delta L, this value here in this formula, so sigma is equal to alpha into delta T into L minus delta divided by L, or you can cancel out this L here. So alpha into delta T minus delta by L will be then into E will be there. So this is the formula for temperature stress in the case of partially restrained. So you have to be careful about the units when you are doing problems. Sigma will be in Newton per mm square temperature stress, epsilon temperature strain, no units. So coefficient of thermal expansion of the material of the ball, it is alpha, some strain value per degree centigrade, then change in temperature delta T in degree centigrade, Young's modulus in Newton per mm square or MPa, A cross sectional area of the ball in millimeter square, L is the length of the ball in millimeters, delta L whether it is elongation or contraction should be in millimeters, gap also should be in millimeters, allowance also should be in millimeters. So the different types of problems which you come across in temperature stresses are they may ask you to find the change in length or strain and also the stress. The other type of problem is they may give the other values. So they may give stress value, they may give increase in length value. So they may ask you to find the allowance that is required, and also sometimes they may ask you to find to what temperature it has to be raised, or to what temperature it has to be cooled. That is delta T value they may ask. So these are the different types of problems we can discuss in temperature stresses. Thank you.